Hi, welcome to the video on this MOSFET problems. So let us look at this CS amplifier designs. In the first one, so we have been asked to find the values of R1, R2 and RD. These are biasing resistors with the specification that the gain should be -5. The input impedance has to be more than 25 kilo ohm, and we are assuming a value of ID of 100 microampere, that is 0.1 milliampere. Of course, the Kp and VTO and W bells are given so and so. So let us try to find out how do we solve this. This is the circuit what we have. So now let us try to write the equations corresponding to this. Let us first identify what is this circuit is. So this is a CS amplifier with source degeneration resistance RS, which is of 100 ohm. We are asked to find what is the value of RD given a value of uh, what the value of AV is given as -5. So let us in this equation we don't know the value of GM, but using this equation of ID under root of 2ID KPWL, we can find the value of GM, which comes out to be 1.414 millisiemens. Using this value of GM and the value of AV as -5, we can certainly find the value of RD, which comes out to be 4.03 kilo ohm. So that is one of the requirement to be found. So we found that RD is 4.03 kilo ohm, and then we are asked to find the value of R1, R2, for which we should know the value of voltage at this point, and then ultimately you can find what is the R1, R2. So for that, let us first know what is VGS. So VGS can be found using the equation, this drain current equation. In this we know everything except VGS. So since this is a quadratic equation, there are two possible values for this VGS, which is which is 541 millivolt, and the other one is 258 millivolt. So these are the two mathematical answers, out of which this is an electrical correct answer, because you cannot have VGS less than the cut-in voltage or the threshold voltage of the MOSFET. So we are discarding this 258 millivolt and we are considering only this. So VGS happens to be 541 millivolt. So that is VGS. Now since we have a resistor RS also, the VG is now given by, you can just have a look at this. So now this is, okay, let me just go back here. So this is the value of VG. The expression for VG here is, so this is the voltage at gate, which is due to VDD and R1, R2. That's what is written here. That's what is VDD into R2 by R plus R2, which is actually equal to the VGS voltage plus ID into RS. So that's what is this, equal to VGS plus ID into RS. We know the drain current as 100, 100 microampere, and RS is 100 ohm. The product of ID into RS happens to be 0.01 volt, and we know VGS is 541. Upon adding these two, we get it as 0.551 volts or 551 millivolts. Upon equating that to this equation, we can write this. Now let us see some conceptual things. The voltage VG that you have here is actually less than the VDD that we are having over here. So you have a VDD which is 1.8. The voltage at gate is due to the potential division of this, but the voltage at this gate is less than half of VDD, that is it is less than 0.9. Since it is less than 0.9, naturally the resistance R2 will be less than R1. So that's what I have written here. So R2 is less than R1 because the VG, which is 0.551, is certainly less than 0.9. So where 0.9 is VDD by 2. So now we know that R2 is less than R1. So when you are writing the small signal model, actually this Rin, okay, I can show you that. So what is R in here? Suppose if I write this, can you see this is the resistance R in looking into a circuit, which is nothing but R1 parallel R2. So when you have two resistors in parallel, the effective resistance is nothing but lesser than the least one. So since R2 is least, we have to ensure that even upon having same resistance over here, this overall resistance should be 25 kilo ohm. So when it is possible to, let me again repeat, R2 is less. So why R2 is less? Because VG is less than half of your VDD. So when R2 is less, let us make this value of R2 so large that when you are making this in parallel with this should yield 25 kilo ohm. So how much large should I keep? If I keep this R2, which is a smaller quantity among these two, if you keep it twice of the minimum, okay, twice of the Rin required, then your Rin can never be less than 25 kilo. So that's why we are assuming, or we are taking the value of R2 to be twice of Rin, which happens to be 50k. When this is 50k, you know what is the value of Vg. Of course, you know this expression of Vg is equal to VDD into R2 by R1 plus R2. So substitute that. You substitute the value of R2 as 50k, you find the value of R1. So when you actually find the value of R1 now, that becomes 113.3k. This is upon calculating. So now let us verify whether this 113.3 kilo ohm in parallel with the 50 kilo ohm, will it be greater than 25k? Yes, it is 34.69 kilo ohm, which is certainly more than 25 kilo ohm. So the entire concept of assuming the value of R2 to be twice of Rin is to ensure that the parallel combination of this R2 and a larger value of R1 will never be less than 25 kilo. So for that purpose, we consider the value of a lesser value of R1 R2 as twice of Rin. So this guarantees me the input impedance is certainly more than 25 kilo. But of course we are writing the small signal model here. So this is, of course you have to be careful here at the source. If we just go back to that circuit, can I open this tool? Let me just open it again and then try to, okay, I can't do that. Okay, let me just open it in my mail and then show simultaneously both of them. Let me see if it is possible. Okay, I hope it is possible. Okay, let me show this here. So let me put this down. Let me put this also down. So what I mean to say is, this is my circuit. This is my small signal model. See now, okay, what we are doing here is, so this is AC grounded. So that's what is AC grounded. Okay, that AC grounded and R1 is also connected to ground. Can you see this? R1 is connected between gate and ground, and R2 is also connected in gate and ground. So this is what is R1, R2. Can you see the input voltage is connected to gate? Can you see the input voltage is connected to gate through a capacitor? This capacitor will look like a short circuit for high frequency. That's why it is replaced by short. Can you see this MOSFET is now replaced by a open circuit between gate and source, and there is a current source from drain to source having a magnitude of Gm into VGS, and there is a RS connected from source to ground. Can you see the same RS is between source to ground? Can you see there is a RD connected from drain to ground here? Of course this will be grounded, this will be AC grounded. That's why we are treating this and this same here. So there is a RD between drain and ground. This is how we can write the small signal model. And let us move on to the next circuit. So in this circuit we are asked to find what is the gain. What is the gain of the amplifier? So it's a straightforward question. So we have been given all parameters and we are asked to find what is the gain of the amplifier. So let us write all the equations corresponding to that. Gm is given as minus Gm into RD. This is also a CS amplifier. Gm is at root of 2 ID Kp into WL. So ID is given by that equation, in which we have to find how much is VGS, that is VGS. So VG is nothing but voltage at gate with respect to ground is nothing but VD minus this drop. So since the current that is flowing through this is zero, why it is zero means because this is a capacitor and this is also an insulator, no current flows in either direction, so zero current is there flowing through this RG. So this is zero. Once IG is zero, this entire current is zero, so VGS is equal to VDD. When VGS is equal to VDD, how much is the ID that will going to flow? So ID is 1.96 milliampere. So after knowing the value of ID, you can put it to this GM equation. You got the GM as 2.8 millisiemens. So once you know this 2.8 millisiemens, multiply that with RD, which is 100 ohm, you're getting a gain of hardly 0.28 magnitude. So that's what is the gain. It is as simple as that. So AC small signal model is pretty simple. Let me show the circuit as well as the model here. So this is your circuit. This is my model here. So let me just drag it down and try to see what is the small signal model. 1 second. This is the small signal model we are talking about. So this is RG connected from gate to ground. So this is RG connected from gate to AC ground. This capacitor is shorted. This capacitor is shorted here. This is shorted. And between gate and source it is open circuit. Between gate and source it is open circuit. And between drain and source it's GM into VGS. So this is what is VGS here. And you have a RD from drain to ground. This is from drain to ground. So that's what is the small signal model. Okay, let us move on to the third circuit, where you are again now asked to find the gain of the amplifier. So it is, you are asked to find what is the gain of the amplifier. So this is a bit interesting. If you can see now, there is a resistor connected from drain and gate, which is 100 kilo ohm, 100 kilo ohm. So we are asked to find what is the AV of this. So before we start writing the equation, first let us write the small signal model of this. So this is how the small signal model will look like. Now we actually had a resistor from gate to drain. Okay, let me just show that over here. So what is the actual circuit? In actual circuit, you have a resistor from. Okay, 1 second. Sorry for that. I have a resistor between. See, where is the resistor? This is actually between gate and drain. So there was a floating resistor. So we know from the Miller's theorem we can replace a floating resistor Rg by Rg1 on the input side and Rg2 on the output side. So at the input side the resistance happens to be Rg by 1 plus AV, and on the other side it is Rg by 1 plus 1 over AV. So when I say 1 over AV, I'm just taking the magnitude. So in the actual circuit it is ZF by 1 minus AV. So because we have a negative gain here, I'm writing it as plus, so that that equation doesn't change. So now this is the equation for Rg1, this is the equation for Rg2. But we know Rg, but we don't know what is AV. So then what is AV expression? AV expression is nothing but it is GM into VGS multiplied by the parallel combination of this RG and RD. So that's what I'm written here, and this is what is written here. This is RD, and this RG2 is 1 plus, sorry, RG by 1 plus. Okay, this is what I've been actually 1 over 1 plus. This is 1 over, this should be 1 over AV, 1 over AV. I hope I have done this calculation wise. I think it is done properly. So let me just find out whether I have done that. Okay, let me just find out that value later. So let us come to this GM. So this is the expression of AV. So GM is straight away given, okay, as under root of 2 ID Kp into W by L. We know what is ID, how much is ID given. I think ID is given as ID is not given. We are supposed to find the value of ID. That's what we are finding here. Can you see, this is the equation, and VGS is given by VD minus ID into RD, which is over here, and we found there are two possible values. This is not a possible answer. These two are mathematically equal, but this cannot be the so, because you have hardly 1.8 volt and you cannot have a drop of something like this large voltage. So because you have a RD of how much? RD is of 1k. RD is of not 1k. Where is that? Okay, RD of 1k. So this is RD of 1k. There cannot be a current of 2 point something milliampere flowing, because that will exceed the supply voltage. So that's why we are discarding this answer and we are considering only this answer. Then GM comes out to be this. Okay, this let me just try to find out. I think I made a mistake here. This would have been Rg by 1 plus 1 over Av. Let me just do that. So sorry for that. So this Av comes out to be, let me do that. It is alpha A. Alpha equals, how much is gm? Gm is actually 2.87. 2.7 multiplied by RD inverse is 1 exponential 3 inverse plus Rg is actually 100 exponential 3 divided by 1 plus alpha A inverse close another inverse. Okay, why alpha A inverse is because I took it as A inverse, and then close, and then one inverse, shift can AV conservative 2.87. So there is a small mistake here. This will be, wait, okay, let me just make this will be 2.87. This value is not 2.76, it will be 2.87. That is one small mistake that has happened. So this is actually Rg2, which is nothing but Rg by 1 plus 1 over Av. So this is one small mistake. So this happens to be 2.87. This is 2.87. So that you can consider. So this is how you can able to consider a design even having a resistor which is between this and this, between the gate and the drain. Thank you.